from now on, we would like to start the Q&A session. And if you have any question, please write in the chat. As we can see, we have already got a few questions from Professor Basandesh. Let's read a few of them. And the first question he asked was from Mr. Julian and about the cost of 4,500 USD. Is this limitation for tether only or power beaming too?
So this cost estimation was for the climber design. So the climber design itself, we estimated the cost to be about 4,500 US dollar, without any sponsorships or parts being manufactured in a collaboration. The power beaming cost, as I said, will be in the power beaming presentation and is additional.
Okay, great. So yeah, thank you for the answer. And next is for Ohno-san, and the question is for beginners, which design of climber is good to start for the competition?
I think every kind of climber would be good. So once you get knowledge how to use the roller against the tether to get the friction is the key point. And for example, so in Japan, so some elementary school children would use the Lego to climb up the small belt, or for the junior high school student, they will start with the motor or roller or those things from radio control car kit. So the brand Tamiya is very famous in Japan, but such kind of radio control car kit includes the motor, battery, charger, motor controller. So the tire, it would be useful to use as the roller against the tether. Then, and such kind of preliminary test climber would be good to start, I think. And then once you get the knowledge or the technique to get the friction against the tether, then it's the it depends on you how scale would you try to build.
Okay, thank you for the clarification. And next question is, I think, to Mr. Simon. As you offered PCB, how much does it cost?
No. So the exact cost is not known yet. We're still developing them. I think, Mordy, if you know anything more about that. However, the cost of production will probably be fairly low. So we don't expect them to cost too much. Let's say this is a very competitive option compared to your regular microcontrollers that you could get.
Okay, thank you. Great. So I think the next question is for Mr. Mordy, and it says like, when are you going to start next WSPEC and where it's going to be held?
Thank you. Yeah. So the next the coming competition, we're opening up the applications in the coming weeks. Check out for the website. So do start forming teams now for that. The actual competition itself, the next international competition, is going to be in next year, around August of 2026, and it'll be held in the US. But again, all that information will come out, and we'll send that out to teams. And just to reference what Simon just said about the PCB chips, again, that we'll have all that information out. Check our website, stay on our socials, so you can see and get updated as the information. Thank you.
Okay, thank you. So the next question is to Mr. Mr. Wright, and where I can get proper knowledge about nature of condition on space elevator, and for example, attitude-related gravity force changes, temperature, and ambient pressure, and something like this. So could you please answer?
I think Dr. Wright had to step out, but basically for all that information in general, I think what he would me to mention is you can check out ISEC's website, isecc.org. That was a lot of, all that technical information and everything there. That's a great body of knowledge. And of course, if you have any questions there, you can always reach out to them directly.
And what would the main consideration be for deciding climber drive system? Is it direct or gearbox?
Maybe I'll take this one. So there's different obviously different factors that go into this. Let me turn on the camera. There's different factors that go into this. Obviously one is the efficiency. If I have a gearbox, I have extra friction there. I have a little bit less efficiency due to the fact that the gearbox, is creating friction, is reducing my total efficiency, as well as obviously another thing you have to consider with a gearbox is that it's an extra point of failure. If I don't have a gearbox, it can't fail, if you will. Then another point which needs to be mentioned is obviously financial aspects. Manufacturing gearboxes, especially if you have quite tight tolerances, is quite a difficult task, which needs some specialized tools. And oftentimes getting access to these specialized tools is a little bit difficult. What you can do then is you can get a gearbox just commercially off the shelf, which might then not necessarily ideally fit your specifications, but you can kind of work around that. On the other hand, obviously, most electrical motors and machines are made to produce high speeds at low torques. Which obviously means that if we want to drive a climber with a lot of payload, then we need the exact opposite. We need a lot of torque at obviously ideally high speeds. But if we can't deal with that, the important thing is we need the torque. So obviously, since most electrical machines are made to produce high speeds and low torques, especially the ones that you can commercially buy, a lot of hobby motors. If you think about the applications, stuff like drone motors and electric skateboards, RC cars, all of these things, need high speeds and not necessarily a lot of torque. In these cases, obviously, we then have to compensate that somehow. If we decide to go for a sort of direct drive system, we need to make sure that we have enough torque. And this is actually one of a big issue we ran into on the Kraxler 5.0, is to sort of select a motor which in a direct drive application can provide enough torque for us. And we actually had to go down slightly with the payload. But yeah, basically the idea was for the first iteration of this 5.0 to use a non-geared system, so we have a little less system complexity and stuff like this. And then in the future, if we determine that we want to increase our payload, we can still add a gearbox, but then this will be an extra effort that we can do at a later stage. So yeah, that's the main considerations really. Obviously a financial aspect. It's at the end of the day a trade-off between how much torque your motors can produce and how much torque you need. Yeah, I hope that answers the question.
Okay, thank you very much. So is there any other question? And if you want to ask anything, you could raise your hand to talk if you want to talk. If you don't want to speak, you could ask anything on the chat. And I think we have another question. Okay. So it's like, which sensor board should we use to start? So this question could be for Simon.
Okay.
Yeah.
Again, for me, I guess. So this really depends on your philosophy or how you want to go about it. A good starting recommendation I can give you is a LiDAR. Basically just time of flight sensor, as they're also called. The idea is very simple. If I have an object, I don't want to turn off the blur behind me. Okay, if I have an object, I basically just shoot out a light beam and I measure how long it takes for the light beam to return to me. So I have a certain time of flight that the light took to get to the object and back. And due to the speed of light, I know more or less where the object is in space. These sensors are quite accurate. The issue with them is most of them that you can buy at, let's say, a reasonable price have only a point. So you need to point them directly at the end stop or wherever the tether ends, so the ground anchor or whatever, or you will get an inaccurate measurement. Additionally, they only have a certain limited ranges. So if you have, let's say, longer tracks that you need to do with your climber, this sort of starts becoming not enough alone, especially since we use a Kalman filter. It is very helpful to have constant measurement data so we can constantly update or correct our state or our position of the climber, so where we think our climber is. And due to this reason, for example, we added an IMU, an inertial measurement unit. These can be really cheap if you get small electronic IMUs. The issue with those is they're not well tested and you don't know the exact error functions, but I would say and they have some drift in them. So as the system's powered on, you can calibrate it to a certain point and then it'll slowly start drifting. So your measurements will get more and more inaccurate. The longer you run the system, especially in the position, in the speed, and even more in the position outputs of this, due to the fact that if you have a small error in the acceleration, you integrate this error over time, you get a bigger error in the speed, and then you integrate the speed again to get the position where you again increase your error even more. Yeah, so IMUs are really helpful if you have, let's say, shorter runs, shorter climb times. But maybe as a supplement, as an extra to the LiDAR. And for example, what you can do then is if you have a certain LiDAR position, you can then update your IMU or update a certain bias basically. So how recalibrate, if you will, your IMU. Other options we've looked at are time of flight sensors. Sorry, not time of flight, optical flow sensors. So basically, you can imagine this as a very fancy mouse sensor. At the end of the day, that's what it is. So it just measures basically how fast an object moves past. So you could use this, for example, on the tether. So if you point this at the tether, you could see how fast the tether is moving. Another option that you have, talking about censored and sensorless motors, is if you do have a motor encoder. So if you know how fast the motor is spinning at any given point, you can also from this then infer how far the climber has traveled. Obviously, in this case, you need to consider slippage. So if you slip, obviously the motor keeps spinning, but we don't move on the tether, or even worse, we move backwards. So we slip off the tether. So as you can see, there's really a lot of options you have with sensors. I've mentioned just a few now. There's many more. This really comes down to sort of your design philosophy and what you would like to do with your climber and sort of what certain requirements you have. Obviously, this comes from the requirements, as I've mentioned, as a really important step in the design is requirements engineering. So if you have certain requirements, you will know sort of what the base conditions for your climber are, what it needs to do, and then based on this, you can select sensors. Really, there's no requirement what sensors you should use. This is really up to every team. And this is really something also nice you can see when you have a competition and you have different teams and there are different approaches to what sensors they use and what motor control they use. And if they have a closed loop or an open loop, if they have a bang controller or whatever. So the options are really up to you, and obviously there's some considerations to do regarding again errors, drift, the operating ranges of certain sensors. But this is a fun engineering challenge. We will try at WSPEC at least to provide some certain sensor boards, so you have some base options, but more will be announced, as Mordy has alluded to. More will be announced later on the website and such.
Okay, thank you, Simon. Okay, let's close this session by taking another last question from Basendash Professor. And this question is for, I guess, Ohno-san. And the question is, what kind of tethers used in the competition? Is it
Yeah.
Wright and
Until now,
Shuichi?
until now, the actual definition of tethers are not decided, but until the history of Japanese and German competition, so perhaps that same kind of tether will be used in next competition. And the cross section of the tether is two types of shape. One is the round, so it would be able to call rope, usual rope. And we usually use the 11 diameter rope woven with the Kevlar fabrics. So in Japan, we do not use the Kevlar, but the Technora from Teijin, and almost the same kind of characteristic fiber. And also we use the belt tether, and the wise is 35 millimeter and 2 millimeter thickness, and woven with same kind of Technora, same kind of rope, Technora. So in 2009, when we start the space electric climber competition in Japan, we used the polyester belt, but some climbers, including German climber, get the free rotation and get the heat temperature will melt a half of belt. Then we move to Kevlar such kind of heat-proof material we would use. And to build the climber, so the tether, Kevlar or Technora belt tether or rope material would be expensive. But in usual, all team would be used for practice to use the ordinary belt or rope. And the key point is the ability of climber ability to change the pressure, roller pressure against the tether or rope would be necessary. Then, and in usual, so it would it would not difficult to make a climber and test the climber with ordinary belt or rope in your daily life use. Would be possible to, if the material would change, which each team should study about the friction adjustment and roller pressure adjustment would be necessary. So in the occasion, the climate challenge would be take place in outdoor. And in sometimes the humidity is high or temperature is high or low or such kind of situation, then each team should change the friction or roller pressure. Then each team have to change the pressure, such kind of parameter against the environment and the tether material things would be necessary. Then the wires is 225 millimeter and thickness is 2 millimeter. And for the rope climber, the diameter is 11 meter. It will be standard size for next year. We should consider. We have not decided yet, but that kind of tether cross section shape would be the most possible tether shape for next year.